I'll go ahead and. All right, I'm gonna go ahead and share my screen. Let's go ahead and um share my whiteboard. Just the whiteboard, because that's all I really need for right now. I will probably need to show you. You know what? It's fine. I'll just go ahead and share everything. Share screen, share screen. Here we go. So what I'm gonna go over today is a sorting algorithm that is not on your assignment. It's a very interesting sorting algorithm, and it's called. Whoops, that is thick, thick boy. Okay, we are going to call it Radix Sort. All right. So Radix Sort is a different sort of sorting algorithm. Most of your sorting algorithms, they rate things in terms of the number of comparisons they have to make, and that's the runtime. The runtime for Radix Sort is a bit different. Most times for the sorts we've been learning have been something like insertion, right? That will have O of n squared. That's also the runtime for selection sort and bubble sort. But things like quick and merge, right? We've been learning that their runtime is n log n, and generally speaking, that is our lowest. That is our lowest level limit for the big O runtime for sorting something for generalized sorting. More specific cases can lead to more specialized runtimes, and then if you get to use parallel processors, you can distribute the workload, and that becomes a bit and that speeds up the time. But generally, the runtime is rated in the number of comparisons. So we say that the insertion sort takes n squared comparisons, where n is the size of the list. Quick and merge sort take n log n, where you have where you have log n layers, right? Where you have log n depth in your recursion tree, and each depth takes the entire width of that depth takes n time. All right. Now, with Radix Sort, we have a wildly different runtime, which is going to be, whoops, NW. So we got this weird capital W, which is not it's not constant, it's just W, which I believe is the word size, which is a weird way to say it. But simply put, it is constant in the sense that it's not going to change based on the number of items. It's going to change based on what your inputs are. So, for instance, if we have a bunch, if we're doing Radix sort on base 10 numbers, right? Base 10 numbers like we normally would use, and we're sorting 5-digit numbers, then our sort then our size is 5, right? But if we're evaluating something like strings, right? Then let's say we're trying to radix sort some list of strings, and maybe we've got bean, we've got string, and we've got taco, and we've got and and we have uh let's go with kitties. Our word side in this case is going to be 7 because kitties is the longest word. So the word size is basically how big the biggest thing is. Okay? So in this case it would be 7. All right? It's also unusual in the sense that we are never going to directly compare two items against each other. These guys are never going to be compared directly against each other. They're never really going to be. It's weird like that. You never do direct comparisons. Okay. So and so this is the reason I introduce it because it's a completely different way of doing things. Now we're not going to do it on strings. We're going to just do it on 10 digit sorry, on base 10 numbers, and we're going to do them on 3-digit numbers. So W here is equal to 3. Okay. Um so let's see. Let's go ahead and write some 3-digit numbers down. We're going to do with 402 769 uh let's see, 128, 428. Let's do else. We have 721, 562, 293. And let's just add some more to the front over here. 093, 101, and 404. All right. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers. That's plenty. Okay. So the way Radix Sort works is that if I'm working in base 10, then I'm going to need some cues. Specifically, I'm going to need 10 cues. 1, 2. Let's make them a bit bigger. And we're gonna look at them from the top. You'll see what I mean. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is one of those where it's easier to show you it in action because once you see it in action, you're like, oh, that's how it works. That's fairly straightforward. Whereas if I try telling you, it's kind of less useful. And I label them all with a value of each one of the possible digits, right? If we're working in with strings, right, normal, ASCII characters, we're going to be doing 26 or 52 of these cues depending. So one for each possible value for a digit, okay? And what we're going over here is that over here is going to be the front of the cue, and this is going to be the back of the cue. Make sense? A bit of a different way of seeing things, but this is how when Radix Sort is done physically, this is how it's done. All right. So let's go ahead and look at 404. What we do first is we start by looking at the least significant digit for each number and placing it in the appropriate queue. The least significant digit being the ones place. So 404 goes in here because it ends with a 4. 101 goes in here because it ends with a 1. 402 goes in the 2 slot because it's got a 2 right there. Okay. 769. Okay. 128. 428. 721. 562. 200, right? And 93. Notice that I pre-padded on a 0 in front of 93. In order to do Radix Sort correctly, you sometimes if it's right, if you're dealing with 5-digit numbers, then anything that's not a 5-digit number will have to have those implicit zeros added to the front of them. So 093, which is our last one, goes in here. All right. Now we erase the top because we've gone through all of them. And then what we do is that we go from the leftmost queue to the rightmost queue, from the one with the smallest value to the largest value. Not the largest small stored value, but the smallest value for the key, labeled on the queue. So we go from left to right, essentially. From left to right, we start dequeuing everything. All right. So what we do first is we start with the zero queue. So we go 200. Then we go with 101 because that's at the front of the queue. 101, 721, 402, 562, 093, 404, 128, 428, 769. All right. And so, and what's cool is that it's kind of intuitive to see that basically if you put everything, uh, if you categorize everything by its last digit and then go from the least value for about, then you pop everything out, sorry, DQ everything from 0 and then going all the way to 9, then of course naturally it's going to be sorted by the last digit. All the last digits, right, have been sorted, right? Everybody see that we've got our last digits in sorted order? Great. Okay, of course you do. Now we do the same thing again, but we did it for the least significant digits the first time. So now we're going to do it for the next least significant, right? We've done the ones. So next we're going to do the tens. Okay. So hopefully now you start seeing how this works, right? So first thing we do, 200 goes into the 0. Now 101 goes into the 0. Okay. Now 721 will go into 2 because it's 721, right? We're looking at the middle digit. 402 goes into here. 562 goes into 6. 093, 404, 128, 128, 428, and 769. Okay. And now we just go through and DQ them all again. And what happens this time, right, you'll see as I write them out, right, we've got 200, 101, 402, 404, 721, 128, 428, 562, 769, and 093. There we go. So now if you take a look at the last two digits, they're sorted not just by the middle digit, but they're sorted by the last two digits. So 0, 1, 2, 4, 21, 28, 28, 62, 69, 93. And now we do it a third time for the last digit. All right. And I'll try to go through this as quickly as possible. It's not exactly the most complicated thing in the world. It is slightly tedious now that I've got so many examples, but 200 goes over here, 101 goes over here, 402 goes over here, because again, we're going by the front digit, 404, 721, right? For the hundreds place, we are putting them in the slot that corresponds to the hundreds place. 428, 562, 796, sorry, 769, and then 093. And now, kind of don't really need to show you, but if we DQ'd them, right, and I'll put them in the order they'd come out in, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we can easily see that they are now going to be sorted from least item to greatest item. Now, how long did this take? Well, we had 10 items, right? We had 10 items. Each run took 10 10 NQs, right? And 10 and then we had DQs, right? We had 10 NQs and 10 DQs for each item. for each of the for each digit. So specifically what we had is that we had 3 digits, so it was 3 times 10 approximate. I'll say 10-ish because again, you've got the operations. So you've got the DQ, you've got the NQ operations, you've got the DQ operations, you've got the ability to compare them. But what we've got here is that it took O of n time, where n was the number of items, times W, word size. It was proportional to this amount, right? Throw in your constants or whatever for what you need. But again, we ignore those constants, which is why we call it grows proportionally to NW, right? Now, this is pretty good. And on the surface, it definitely seems better than n squared. And it also seems better than n log n because, I mean, right? This is a constant value. But it's an important constant value because that's why we leave it in. But why don't we see it more often in actual use case? Well, first off, let's see where this was actually used. Non-comparative sorting algorithm, WN, key length. They call it key length rather than word size. Okay. W makes me think word size. But this was a card sorter that did Radix Sort on punch cards, right? This is something you can build to do physical sorting of items if they're set up for it. And it's pretty cool. Okay. And it's definitely worth checking up on, but let's see why it's not used normally. Well, when we're working with computers, right? This example I did was base 10, right? But on the CPU, on the computers, that would be using base 2, which means we have 2 queues, 0 and 1, right? Also, they're base 2 numbers, meaning they're binary numbers, right? And if we remember, and hopefully we remember how big some of these numbers are, right? Ints, specifically, are 32-bit, right? That means they have 32 binary digits, okay? Let's just assume we're working with ints for a second, and 32-bit ints, even though a lot of stuff is going to 64, right? But let's look at 32-bit let's look at writing a generic algorithm using Radix Sort that works off of ints, right? Right? So that means that if we're sorting a bunch of ints, a list of ints, it'll take n times 32, right? Where W is equal to 32 in this case because it is a 32 because these are 32-bit numbers. There's no way to really tell how big these numbers are without adding more runtime, right? You don't want to know maybe if you knew what the maximum size was, but these are 32-bit numbers, and so we would have to sort them. Okay. So this would take n times 32 time, which you're like, okay, but that is a constant, right? For any iteration of the algorithm over ints. So why not use it? Well, the answer is that constant ain't very good here. And again, it's not really. This is why you got to be careful of any time they claim a constant. Let's think about this for a second. If I am doing quicksort, that will take O of n log, let's call it n log n time, where we're using base 2 of our logarithm for simplicity's sake, right? So the question is, at what point, you know, so for what n is log n greater than or equal to 32, right? Because once log n, so why am I asking that question? Log n is normally very small. We're normally doing log times log n. Sorry, n times log n. That's normally a very small number, log n. 32, when is 32 going to be smaller than log n? Because at that point, if 32 is less than the log n, or log n is greater than 32, that's the point where I would want to use radix sort. Well, we can well, fortunately, because we're working with logarithms, sorry, we're working with base 2 numbers, and we're doing logarithms, this actually becomes pretty easy to figure out. And the answer is when n is greater than or equal to 2 to the 32, I'm going to say ish, because again, because again, once you're in big O, we're doing kind of estimates of things. But simply put, 2 to the 32 power, right? Times, I'm just plugging in 2 to the 32 for n. That's what I'm doing. Log 2 to the 32. This is log base 2 of 2 to the 32. That means this cancels into 32. So that means that for radix sort to be the better choice for runtimes, we need to be dealing with more n is where n is greater than 2 to the 32, which is about 4 billion-ish. Hold on a second. Hey, take a look. Oh, fun fact. Okay. You're not going to be able to unsee this. This is the calculator app. And I learned this from watching a YouTube short, of course. But let's screenshot that. Screenshot. And now, no, are you not going to pop up? Well, open up your calendar, your calculator app, and just take a screenshot and zoom in there. That's not lined up. It's not symmetrical there. It's funny. All right, let's go ahead. 2 32. 4 billion. Yeah, so I was remembering correctly. Okay. Now, what are we doing here? Let's see. We've got, so yeah, you need to be sorting more than 4.2 billion items for this to be worthwhile, or to consider it to be worthwhile, which it may not be because our sorting algorithms are pretty optimized at the moment. Like some fun optimizations that we do is like, hopefully you've learned quicksort at this point. Hopefully you've taken the time to watch the lecture on quicksort, which is again fairly straightforward. What you do is you've got this, right? And I mentioned quicksort because that's the one of the ones we put on the final exam almost every single time. That's the one where basically where you figure out a pivot, right? You select a pivot from it, and then we go and translate that into pivot everything less than the pivot and everything greater than the pivot. And then we then proceed to quicksort each of those sides recursively, right? You've learned that. So abstractly, you understand how quicksort work. Hopefully, you've taken the time to learn internally how it works, but that's not how Java does quicksort, right? Sorting Java arrays. Let's go ahead and just look at the arrays method in Java. And if we look at sort, okay. If we look at sort over here for, let's say, integers, okay, you'll see that it's very interesting what it says. It says, implementation note, the sorting algorithm is a dual pivot quicksort by Vladimir Yaroslavsky, John Bentley, and Joshua Bloch. Okay, it does n log n on many other quicksorts that degrade to quadratic performance and typically faster than the traditional quicksort. But you don't necessarily know what clever coding goes on but you know basically what that means, right? That means you kind of understand abstractly, oh, that means we pick some P1 and we pick some P2. And now, right, abstractly, we understand that we've got a P1 here and a P2 here, right? And now we've sectioned it off into thirds where we have everything less than P1. Sorry, where we let's assume that P1 is less than P2 because if they're not, it's super easy to fix that, right? Everything less than P1, everything over here that is where you have P1 and P2 and X is in between them, where X is our number. And then finally, right, X is greater than P2, right? And you understand that's kind of how it works. It splits it off into three branches, right? You abstractly understand, even though you may not know the internal ideas of how that gets done. That's why we try to teach you, you know, an internal a method of doing these sorts in place that works pedagogically. Sorry, that works, and teach you that for pedagogical reasons, without having to like spend a ridiculous amount of time learning how to do this. Because if you're interested in the details, you can look that up, but you know enough about quicksort in general now and the pivot method that you can just look at this. Another and then why do I teach you two sorting algorithms? Why am I teaching you quicksort uh and merge sort? We look at parallel sort, but let's go ahead and look at sort, and that should be T, not parallel sort. Sorts the array of objects. Here we go. Sort object. So when you're dealing with primitives, Java uses quicksort. But when you're dealing with objects, stable, adaptive, iterative. So typically what it's using is a version of merge sort. Typically it's using Tim sort. That's what's using there. So you use Tim sort for objects, and for quicksort you use for primitives you use quicksort. And part of that is, I believe, because you need it to be stable. Stable meaning that it will be, I'll say, I believe stable stable sorting algorithms. I'm going to say this and then I'm going to double check myself, which is always dangerous. But for a sorting algorithm to be stable, basically, if you have best way I can describe it is that if you have a king of hearts and a king of clubs, right? You have a list, you have a deck of cards, you have a king of hearts, you have a king of clubs, right? Then when we get our output, the king of hearts is going to be before the king of clubs. They're not going to change spaces, even though they technically have the same value, which is king. And similarly, if king of clubs was before king of hearts, then in the output, we would get king of clubs, king of hearts. They don't change spaces based on that. I was right. Stable sorting algorithm preserves the relative order of equal elements. All right. And for numbers, that doesn't really matter, right? It doesn't matter whether it's whether it's that or not, right? There's no difference between this 5 and this 5 than possibly one of these being more aesthetically pleasing to your eyes, right? There's no value difference between them. The sorting algorithm does not care. And so it doesn't matter which of these comes first or second. But for other values, it matters. All right. So that's what I've got for you today. I just wanted to go over Radix Sort and just go over, because it's a very interesting sorting algorithm. And I wanted to, uh, just kind of just give you some more insight into sorting algorithms and why we teach these. Um, a lot of problems with data structures, or sorry, a lot of problems in this class basically are, oh, this problem becomes a lot easier once I know how to apply the appropriate data structure. Similarly, a lot of problems become a lot easier once you realize, oh, I can sort the data. All right, with that, um, I'm more than willing to help you on programming. So typically what I do is I stick around and people can share their screen. I can split us up into breakout rooms if necessary. Um, but I can share but you can, but I'll enable screen sharing that you can, so you can share your screen and I can help you on anything you're stuck on.